in there, so we need to have some things in there so we can move on and then use that information. So I'm hoping that those 4 questions, maybe a bit rusty after the summer, but we're going to go through them now, and that's the sort of information I think you need to have in your head. So if you're struggling with some of these things, the video clips are there, the textbooks are there, you've got to work at it, okay? Even more this year than last year. It's no good just coming along to the maths session and then working in this session and putting your books away until you come along next week and expect to do okay at this. Okay, you need to put in a bit more practice than that. So the first one is all about remembering Ohm's law. Anybody? V equals IR. So that's it. Oh, just hang on, let's just pause 1 second. Right, that's better. So V equals IR. I want to find I, so I've got to rearrange this formula for I. Jack? What does I equal if I rearrange this formula? V divided by R. Good. So that equals, what's V? 3.64 times 10 to the 3 divided by R, which is times 10 to the 6. Yeah. Plug that into the calculator and you get 38. Thank you. Do you remember we were talking about last year about this idea of estimating to get whether or not to check whether or not these things are right? Because the problem with putting numbers like this into the calculator is, first of all, what does a number mean? So that's actually times 10 to the 3 means times 1,000, so that's really 3,640. 10 to the 6 is a million, so 5 million, 5.7 million. Okay? So I'm going to expect a reasonably small answer, but I can do a bit better than that. I can sort of round this to one significant figure. So this is roughly 4 to one significant figure. What's that to one significant figure? So 4 divided by 6. And then what do we do with the powers if I divide? Right, so that's roughly 4 divided by 6, which is 0.2 thirds is 0.66. It's roughly 0.6 times 10 to the 3 take away 6 is minus 3, which is the same as 6 times 10 to the minus 4. So if I was doing a little calculation in my head, I'd be sort of expecting something to the minus 3 or minus 4, and I get that. So 6 times 10, that looks right, okay, when you do it on the calculator. Is that an appropriate accuracy? No. We look at this, 2 significant figures in the resistance, 3 in the voltage. Remember the rule? It's the same significance as the least accurate figure you put in, or maybe one more. So we could go to 2 or 3 significant figures. So what would you round that to? 3 significant figures, what would it be to 3 significant figures then? To 3 significant figures, so that makes that 5 comes in, so 639, yeah. Ben, if it's 5 or more, we can round up. Times 10 to the minus 6. Why did you go to minus 6? Interestingly, because it's an engineering notation. Excellent. So we could have gone twice that way, which means this should become minus 6, and then round it to, or we could have gone the other way and called it 0.6 times 10 to the minus 3, couldn't we? Yeah. 2 significant figures?
640.
Yeah, right. Yeah. Or 640 times 10 to the minus 6 to 2 significant figures, 3 significant figures. You remember we spent a bit of time on this at the beginning of last year talking about this accuracy, so I'm assuming that now, that you're going to be able to bang these numbers into the calculator, that you might have a go at roughly estimating it so that you know that when you do it on the calculator you've done it right, and you've also going to give your answers to an appropriate accuracy, not just whack out loads of decimal points. Okay? Right, so that's number one. Any questions on that? Number two, I heard somebody mention SOHCAHTOA over here. That's what's involved. So it's to do with sines, cosines and tangents. H hypotenuse, O opposite, A adjacent, S for sine, C for cosine, T for tangent, SOHCAHTOA. So which one is involved in this particular case? Right, the adjacent, because it's next to the angle, and so it must be that one. Okay, so cosine of theta equals adjacent over hypotenuse is the actual trigonometric relationship. So this is reminding you that sine is opposite over hypotenuse and tangent is opposite over adjacent. Okay, so the cosine of the angle is the adjacent over the hypotenuse. I expect you to know that, so not to have to look it up all the time. Remember this thing. Okay. So we're after the adjacent, so I've got to rearrange this formula a bit, haven't I? What does the adjacent equal? Get the adjacent on its own. What does the adjacent equal? Well, the formula I'm after, I'd have to multiply both sides by h, so it's going to be the hypotenuse times the cosine of theta. So that's the stuff that you need to remember, that this is the relationship you're after. I've got to rearrange it slightly to get the adjacent side, and now I can put the numbers in. So the adjacent equals the hypotenuse, which is 15, times the cosine of 45 degrees. So now if you'd just like to do that on your calculator. And you get 10.6. Have you rounded that? Yeah. So that's the three significant figures, is it? Appropriate number of significant figures? Yeah, that's 2, so you could go to one more, so 10.6 is reasonable. Everybody get that? No. That's not theta again. Theta. I just wondered if anybody got a different answer, because there's one danger here. What's that? When typing this in. Yeah, but you might be in radians on the calculator, so I was just wondering whether we got a different answer. So if you're all in degrees, you'll be okay. But of course, you might be working in radians the last time you're using it, so you've always got to be aware of that, okay? Yeah, times the cosine of the angle, yeah. Okay? That sort of question, I'm assuming, if you're in the middle of some other problem where something else has got to be calculated, you could easily just do that, because it's just basic trigonometry. Well, next question. What we have here is a situation where we've got group data, so what have we got to do with this group data before we can find the mean? Find the middle, yeah. We need the midpoint. The midpoint of that group is 5, 15, 25 and 35. Not between, what's halfway between 11 and 20? That's not 15, isn't it? But really you're thinking of halfway between the end of the previous group and the end of the group you're in. So it's halfway between 10 and 20, not really 11 and 20. So as long as you make them sort of consistent, it doesn't matter. Yeah, it doesn't matter too much, but that's the sort of way I So that makes the numbers nice and easy for a start off. And then I've got to generate another column, which will be, what have I got to do to be able to now find the median? No, I want the mean altogether. I've got 4 of 5s and 8 in this, of 8 in that group, and so times them together. F times the midpoint, so that would be X, the midpoint. So 5 4s are 20, and so on. Okay. 8 15s, 2 15s are 30, so 4 30s are 120. 3 25s are 75, and 1 35 is 35. Once I've done that, what do I do with that? Add them together to get what's called the sum. Yeah. Well, if it's age, the mean value is the sum of fx over the sum of f. So the mean is the sum of fx over the sum of f. Remember we were doing that in the statistics assignment we did. So you've all done this, it's just remembering it. So add them together. That's 110, 230, 250 over 12, 16, you're right. 250 divided by 16 is, and there's your mean. 15.625. So we're going to round it, aren't we? Because so we'll probably call it 15.6 maybe, okay? Or 16, depending on what it is that this is representing. If this data is only representing whole numbers, then we'd round to the nearest whole number and call it 16. Okay, so it all depends on what you're measuring. And they are all whole numbers, so that's a reasonable thing to do. Okay. Okay. Yeah. Okay, last question. Actually put this one in because the first thing, or one of the first things we're going to be looking at is actually representing functions using graphical software, and so that's where we need autograph. And so I just thought I'd introduce that by way of showing you a curve and wondering whether or not we can recognize it. This is a parabolic curve. So it represents an x squared function. So the x squared in here, I'd expect to see. But they've all got x squared in. So the next question to ask yourself is, what do I do about the fact that it's this way up? I just use this so we can, that it's this way up rather than like that. What effect does that have? Does it make it positive or negative? And the next thing is, what do we do about this? Look, the fact that it's not crossing at 0, it's crossing here. So when x is 0, y has a value. So which one best describes that curve? A, B, C, or D? Well, not A, because we need, if x is 0, right then, if x was 0, what's the value of y? So it can't be that because it's not 0 here, is it? So that limits it to C or D because it's got the B in it. The only question now is it B plus AX squared or B minus AX squared? If I add the x squared, if x is getting bigger, what's going to happen to B plus AX squared? Is that what's happening? No, it's not, is it? So it must be D, okay? Y equals B minus AX squared. B represents a number, a value. So in other words, B is this point here. This point here is B. Because when x is 0, y equals B. Okay? So recognizing functions, how do you do it? You get to know the shapes, and we'll talk about that. And you also look at where it crosses the y-axis is often a very interesting point as far as a function is concerned, because that tells you straight away whether there's a constant involved. And then you may be interested in where it crosses the x-axis as well. Okay. So that's the aim for today, calculating standard deviation. What does it tell us, and how do we calculate it from a set of data? So what I'm going to do is look at an example of a set of data and take you through how you calculate the standard deviation and what it tells us. Well, let's go back so you can make a note of that if you want. That's the aim for today. Okay. So, yeah. Right, so this example, make a note of it. You're going to make a table. And leave yourself room to the right because you're going to add columns. So, a set of data. 1, 2, 3, 4. And then I'm going to add columns down there, so leave yourself room to do that. So, here are some measurements, could be 34.42, 50, 55, and 60. Frequency. So I don't want to overdo the numbers that are involved here. It's the principle that we're interested in, so quite a small data set. So X represents the data and F represents the frequency, which you know. When you've got a set of data, we normally quote two figures. One is the mean, and we've already looked at the mean, how you calculate the mean, so I'm sure you could do that. The other piece of data that we're interested in is how far away from the mean the data is roughly. If you think about doing a statistical analysis on something, if you're doing it at work, and you had a whole set of data, which could be the lengths of some components you're making or the mass of some components you're making, and you wanted to keep those components within a certain tolerance band, if the statistics department at your firm did a survey on that and they came up with a mean mass or the mean length of these things, that wouldn't really be enough. You'd want to know something about the spread of the data. Are there loads much smaller and much bigger, which would be bad news if I want them all to be roughly the same size. Okay? So two figures are normally quoted, the mean and the standard deviation, which is what we're interested in now. So how do you calculate the standard deviation?
Is that what the range?
Yes, it's to do with the range. The range is a very rough measure, which is just the distance between the smallest and the biggest. But what we're interested in is an idea of how far each piece of data is from the mean. So if the mean comes to be around about, say, 34.5, which is roughly in the middle here, how far away are these other pieces of data from the mean? Is it very spread out, or are most of the data quite close to the mean? So if you think about it, what we could do is measure the mean and then look at how far away each of these bits of data are from the mean by doing a little subtraction. If the mean was, say, 34.5, well, what's the distance of 34.42 from the mean? Take one away from the other, and so on. And then when we've got all those differences, find the average of those, add up all those differences and find the mean. And that's effectively what you do with the standard deviation. It's called the mean of the deviations. Deviations meaning how far is it from the mean. And so this is what we're going to do. So what we do is, we find the mean first of all, we need that value. So the first column we need is where we multiply the frequency by x. So if you generate that fx column for me and then calculate the mean, please. Okay, so the mean is 34.53, calculated by generating that fx column. So now what we want is to subtract the mean from each of these values. So what I want now is a column where I take away the mean from values, x minus the mean. So I take 34.42, which is the first value, and subtract 34.53. Even if you get a negative answer, yes, Ben. So 34.42 minus 34.53 is minus 11, minus 0.11, is it? And so on. So if you can, again for this one, subtract x from the mean. 34.5 minus 34.53 is minus 0.03, and so on. 0.02 and 0.07. X minus the mean. Look at these values. You remember what we're after? We're after some sort of number that's going to indicate for us how far away the value is from the mean. And that's, you can see, the further the data is from the mean, the bigger this number. So it's giving us an idea, isn't it? Okay. The trouble is, some of them are negative and some of them are positive. Hang on, I'll just pause while these guys finish faffing about. What we have is some numbers that represent how far away, some positive, some negative. A lot of statistical, well, most statistical surveys you do actually turn out to be nice and evenly spread. About the mean. So in theory, I'd have just as many negatives as positives. So if I were to try and add them up to find some sort of mean, the negatives would cancel out the positives and I'd end up with 0, which would tell me that the data is nice and evenly spread, but it wouldn't give me any idea about how big the spread is. So I need to get rid of that negative sign, and what we do is we square, because whenever you square a number, you get rid of the negative sign. So the next thing I do is square it. X minus the mean squared. So I take each of these values. Because I know it's going to turn out to be positive, don't worry about the negative sign. Just square 0.11, 0.03, and so on. You don't want the negative, right? No. I think that should be 0.009. I think I've done those right, but check for me. I'm not sure what that one is. 131, 0.0131, is it? 9 times 10 to the minus 4. You mean stop it doing that on the scale? I'm not sure how you do it. I think you have to press a button and sort of, yeah. Is it? Oh yeah, 121, yeah. 0.0121, yeah. Okay, so now, if you think about it, we've got a positive value, and again, the bigger the number, the further we are from the mean, which is, so it's still giving us an idea of what the spread is. We now have a situation where we've got this piece of data, the 34.42, that far away. That's giving us an idea how far away that piece of data is from the mean, and so on. But of course, we've got 3 of those. So what we want to do now is add up all these deviations. Remember, we're after the mean of the deviations. That's what the standard deviation is. So I need to take into account I've got 3 of those and 4 of those and so on. So time them together. So now I need another column where I multiply the frequency by x minus the mean squared. And that's the last column we're going to need. Add them all together. Divided by the number. So yeah, we're after the sum of f x minus the mean squared. And so the standard deviation and the symbol for standard deviation is sigma, small letter sigma, which is that circle with a line on it, sigma. So the standard deviation equals, defined as, the sum of f x minus the mean squared over the sum of f. To correct, the variance equals this, not the standard deviation, no. So the variance is 0.00437, which gives us an idea how spread out the data is. However, that's not the full story, and in fact we need the variance. For some reason this assignment asks for the variance, but not a very useful statistic, because we manipulated the data to get rid of something to get this figure. We manipulated the data by squaring to get rid of the negative sign. So we could really at the end do with undoing that. So we take the square root of that to get rid of the squaring effect. Yes. So the standard deviation, so now we can easily find the standard deviation. The standard deviation, yeah. And that's that symbol sigma is the square root of the variance, as Josh says. And so sigma equals the square root of 0.00437. Sigma. 0.661. Correction, 0.0661. To recap, you're going to be asked to do this in the assignment. We can easily find the standard deviation. We just need to set out a table like this, where we have x and f. We need to talk briefly next time now, because we run out of time, about what we do if it's a group data set, but I think you can imagine what you do. Okay? And then once we've got that, we generate the fx column to find the mean. Then we're after how far the mean is from each of the data points, so x minus the mean. Then what we do is we square it to get rid of the negative sign, and then we take into account the fact that we actually got a frequency for each of these pieces of data, so we multiply the frequency by the x minus the mean squared, and then it's just straightforward after that. It's finding the mean of those variances. So we add them all together and divide by the sum of f, and then finally, that gives us the variance, finally, to get the standard deviation, we square root the answer.
We still aren't getting that thinking shot now, because our square root number, if you reverse that back, the answer is 0.11. 0.11, not minus 0.11.
No, but what we're only interested in the size of it, not the sign. So by squaring it,
So
we get rid of that.
Whatever side of the zero, you don't really care.
Yeah, that's right. Yeah, how big is the data? Exactly right. So, and actually that leads me to the next point that I want to make, or the final point. We just have to take the midpoint.
You said to find the midpoint.
Yeah.
Yeah, bring it back, don't we?
Yeah. That's right. Yeah.
But this one, you thought we got that one.
Okay. Now, just to finish this off. For big statistical studies where you've got lots of data, so in an engineering environment, large statistical studies done, say, on the size of the components. So we're sampling a very big quantity of material. We end up with, unless there's something unusual going on, which is causing distribution. I'm trying to talk and write at the same time. Distribution. We find that the data is normally distributed, and this is a function, this red line. Think of the function we looked at in the drill. There is a mathematical formula that would talk about that function, and we can write down what that formula is. I'm not going to. It's got an exponential component to it, but quite a complex function. But if there is a function that describes this curve, which there is, we can then find the area under the curve by integrating. We looked at that a little bit last year, more of that this year. In other words, we can find out by playing around with this function how much of the data is exactly underneath by finding the area underneath the curve. And we find that when we do that, every time we do it, around about 67% of the data lies within one step. I'll have to get this up. Perhaps you could club together and all buy me a wireless one of these. We find that 67%, near enough, 2/3 of the data lies within one standard deviation either side of the mean if the data is normally distributed. So what we have is, there's the mean, x bar in the middle. We've got one standard deviation this way and one standard deviation this way. We'll then describe 67% of the data. So if we think of our problem, we've got a mean. So for our example, what was the mean? 34 point, what was the mean, Ben? And the standard deviation is? Right, so that means if I add 0.0661 to 34.53, so this is the mean, 34.53. Yeah, that's right. So what's 34.53 plus 0.0661, quickly, somebody?
34.59661.
59. And 34.53 minus 0.0661. For something or other. Something or other. Okay. 4639, is it? So near enough 47. Okay. So what we then can say is that 2/3 of our data lies between 34.47 and 34.6, near enough. And if we look back at our original data set back here, and we can sort of see that 34 point up to 34.6 roughly. But it doesn't work for this data particularly because this is such a small data set. For this to start to happen and for you to be able to say with confidence that this is actually correct, that most of our data lies between these 2 points. We need a large amount of
With
data.
that one as well, you've also got the most frequency in the highest.
Yeah, so it was a bit of an unusual data set, that's right, yeah. Okay. Okay. So next time, we'll have a look at what we do with the groups. We'll start off by looking at that example, but there's nothing to stop you having a look at some of these exercises on the here. If you've got the textbook, that's asking you to find the standard deviation, basically, just to practice what we've just been looking at today. If you want to have a go at that between now and next week and give them to me, then I can give you the assignment. Okay? Right. We'll stop there.